In this module, we introduce the concept of entropy and formulate the second law of thermodynamics. The observed asymmetry between spontaneous and non-spontaneous processes is captured by the second law of thermodynamics. Multiple, seemingly unrelated formulations of this law have been proposed. However, we will focus on the one that incorporates the concept of entropy. Among the various ways entropy can be introduced, we will adopt the thermodynamic definition as formulated by Rudolf Clausius. Following Rudolf Clausius, entropy is introduced through its infinitesimal change, ds. This change of entropy occurs due to a physical or chemical process. ds equals delta Q rev divided by T. Here, the letter D in ds signifies that entropy is a state function. In contrast, the heat exchanged between the system and its surroundings is a path function. This is indicated by using the symbol delta for an infinitesimal increment of heat. Now you might wonder, how can a path function be converted into a state function? Two key aspects make this possible. First, we consider the heat transferred to the system reversibly. That means in a reversible process. Second, this increment of heat is divided by the absolute thermodynamic temperature T. The outcome of this transformation gives us a change of a state function. Note that since the heat exchanged between a system and its surroundings depends on the system's size, entropy behaves likewise. This means entropy is an extensive state function. The dimension of entropy is energy divided by temperature, and its coherent SI unit is joule per Kelvin. If the system in question is a specific amount of a chemical substance, we can introduce molar entropy as m. Molar entropy is an intensive state function. Its dimension is energy divided by temperature and amount of substance, and its coherent SI unit is joule per Kelvin per mole. So, how can we calculate the entropy difference between two states, 1 and 2? The finite difference in entropy between any two states, 1 and 2, is calculated as an integral of ds along a path connecting these states. From the definition of entropy, we infer that to calculate this difference, we must first identify a reversible path connecting the states. Then we must integrate the infinitesimal change of the exchanged heat divided by the current value of the absolute temperature along this reversible path. As entropy is a state function, its change when going from state 1 to state 2 is path independent and remains the same regardless of the specific reversible path taken to perform the integration. Importantly, the change of the state function entropy in a process going from state 1 to state 2 is the same regardless of the actual path taken, be it reversible or irreversible. Thus, even for an irreversible transition from state 1 to state 2, the entropy change matches the difference calculated using a reversible path. Having introduced the state function entropy and detailed the method to calculate entropy differences, let's now formulate the second law of thermodynamics for an isolated system. In an isolated system, the entropy increases during a spontaneous process and remains unchanged during a reversible process. This leads to several important implications of the second law for the entropy of isolated systems. The entropy of an isolated system never decreases. It either increases or stays the same. In an isolated system, irreversible processes continue until the system transitions from a non-equilibrium to an equilibrium state. The equilibrium state for such a system is characterized by the maximum of its entropy. These statements provide answers to the questions posed in our earlier discussion. For a closed system, we can consider it and its surroundings together as a globally isolated system. Then, the second law of thermodynamics can be formulated as the combined entropy of a closed system and its surroundings increases during a spontaneous process and remains constant during a reversible process. This implies that the entropy of a closed system can decrease during a reversible or spontaneous process. However, it must be offset by an increase in the entropy of the surroundings equal or greater than the magnitude of the system's entropy decrease.